8.3, example 5. In this example, we're going to show how rates have a transitive relation. So this is a definition of growth rates. And the definition is that growing at the same rate is a transitive relation. So this is what I mean by that. If f grows at the same rate as g, and g grows at the same rate as h, then f grows at the same rate as h. So again, if f grows as fast as this, and if g grows as fast as this, then f grows as fast as h. It kind of skips the g. Okay, so example 5, we're going to show that the square root of x squared plus 5 and g of x, which is 2 squared x minus 1 squared, grow at the same rate. So just setting this limit up and then doing L'Hopital's and all that stuff would be a lot of work. So I do want to point out some things before we do get started though. So I want to point out first that the square root of x squared is equal to the absolute value of x, which is equal to x as x grows to infinity, right? Because the absolute value of x looks like this. So as we go to infinity, it just looks like regular old x as we're approaching infinity. So by that logic, 2 square root of x squared is 4x, which pretty much grows like x. 4x grows like x. They all go to infinity. So both of these can be just summarized as x grows to infinity. Okay, so by this logic, we're going to let our h of x equal x because it has the same end behavior as the square root of x squared and 2 square root of x squared. So notice that both of these kind of have the same end behavior as x. So here we go. So to show that something equals a constant, you're going to do the limit as x goes to infinity of f of x divided by g of x. Okay, so this next step is going to seem kind of weird. We're going to do limit as x goes to infinity. I'm going to divide f and g both by h. So I get f of x divided by h of x divided by g of x divided by h of x. And just doing the algebra to make this a little easier, it's the limit as x approaches infinity of f of x divided by h of x times h of x divided by g of x. Again, if we cancel the h of x, we're left with what we started with. So this is the limit as x approaches infinity of f of x divided by h of x times the limit as x approaches infinity of h of x divided by g of x. That's the limit properties in effect. So what we're going to do is we're going to find these two separately, and then we'll multiply them at the end. Okay? So the first one we're going to go ahead and work out is the limit of f of x divided by h of x. And recall f of x was the square root of x squared plus 5, and h of x was x. Okay, so I can rewrite x, and again, this is using some fancy algebra here. I can rewrite x as the square root of x squared. Because we're going to infinity, they have the same end behavior, and they're practically the same function. So then I can write the whole thing underneath the square root. And then from there, I can get this as the limit as x approaches infinity. X squared divided by x squared plus 5 over x squared. So this becomes the limit as x approaches infinity. The square root of 1 plus 5 over x squared. You plug in infinity, and the 5 over x squared goes to 0. So then I'm left with this is the limit as x goes to infinity, square root of 1, which is 1. So the next piece we need to find is the limit of h of x divided by g of x. That's that second piece we wanted to find. So this is the limit as x approaches infinity. H of x was x divided by 2 square root of x minus 1 squared. So this is the limit as x approaches infinity of x. And then if we distribute the denominator out, we're going to get 4x minus 4 square root of x plus 1. And then using our end behavior models, so the end behavior model for this is just 4x. So that's using those end behavior models. So limit as x approaches infinity of x over 4x. Our x's are going to reduce off. And we get that this is the limit as x approaches infinity of 1/4, which is 1/4. Now we have one final step, which is to put it all back together. So recall it was the limit as x approaches infinity of f of x divided by g of x, which we simplified down to f of x divided by h of x times h of x over g of x. So we're going to split up that limit like we set it up previously, so it looks exactly the same. Limit as x approaches infinity of h of x divided by g of x. And we found that the limit as x approaches infinity of f of x divided by h of x was 1. And the limit as x approaches infinity of h of x divided by g of x was 1/4. So 1 times 1/4 is 1/4, which is not 0. So since the limit as x approaches infinity of f of x divided by g of x is not 0, these two functions f and g grow at the same rate.